Can you hear me?
Yes.
Okay, thank you. So greeting of the day. I know that we have a lot of attendees across the globe. And I'm pleased to be part of this virtual conference. And so today what we'll do is we'll look at machine learning, how we can do machine learning on constrained IoT edge devices. So the outline of the talk is first we'll introduce and motivate the problem, and then I will report two results that we have regarding using machine learning on constrained edge nodes, and then we'll draw conclusions. So what is IoT? So we already know it's from the previous two talks, is really the effort of connecting the unconnected. And so the goal is to connect the unconnected, and this is not really a new technology, but rather it's a technology transition. So it's using existing technologies, bringing them together so that the promise is that you have more efficiency, you can automate, less wastage, right, and you can enable advanced applications. So the IoT World Forum standardized architecture defines 7 layers, and really the lowest layer is the physical devices and controllers. We can look at that as the edge, where sensors are collecting data, and in a simple IoT solution, probably they are just collecting data and sending across the network through these layers to your cloud, where the data is stored and then used. Okay, so that is a simplistic model. So now, why should we, what do we mean by edge computing, and why do we need that? So why can't we just have simple sensors collecting data and then just sending it to the cloud server? So this is not possible, because in IoT system, we are talking about, in a large IoT system, we're talking about tens of thousands of edge devices, and perhaps millions. If you are, for example, looking at a smart city, so there is no way you can get all the data to the cloud, all the time, because the sensors are collecting data continuously. So we need because of limited bandwidth, we need to reduce the data that needs to be sent. Second is that the data privacy. So some of the data, for example, in smart health, when it's collected, we don't want to send that data across due to privacy reasons. And somehow, if we can filter it at the edge and anonymize it, that would be better. And of course, if you are going to store the entire raw data, then that is going to be in the cloud. That's going to be not possible, because the storage, even though we have vast storage, still for a practical IoT system, we don't have enough storage. And of course, there are other things like by computing on the edge and doing more processing at the edge, we can reduce the cost, we can reduce the power consumption on the network as well as the cloud. So now, what is machine learning? So machine learning is is a subset of a broad field of AI, or artificial intelligence. So machine learning is you are trying to improve performance of a task, as Tom Mitchell has defined. It's machine learning is study of algorithms that will improve the performance of some task that you want to, some problem that you want to solve, especially with some experience that you have. Just like humans, with experience, we become better at doing things. We are trying to mimic that in machines. So why is machine learning important? Because the computations these days, so the computing has become cheaper thanks to Moore's law. We are able to process more data at a faster rate, store data in large volumes, and we can also automate some of these tasks. So machine learning, so this is the time when we can actually think of building intelligence into these devices. So instead of them being passive, they can be active. They can actually be intelligent and filter the data. So the intelligent filtering actually solves some of the problems that we talked about earlier. That is, it reduces the data footprint, and of course, most important is that we don't want to lose information. So that is very important. So it has to be intelligent. We don't want to lose critical information. Okay? So we only lose noise, right? And there are a variety of machine learning algorithms that we can consider. And typically, a machine learning algorithm has a training, that can happen on the cloud, and training still is a very compute-intensive problem. So with today's technology, we cannot train, on the edge. But however, we can infer on the edge. Okay, so once it's trained, we can deploy it on the edge devices and use that to intelligently reduce the data. And here, this plot here shows from one of the authors, on convolution neural networks, how in order to increase the ImageNet accuracy, the number of operations that you have to do, that you have to perform, they're actually increasing, exponentially. So this is a log scale, so it's increasing exponentially. So this underlines, like, especially image processing algorithms on the edge, you need more computing power. So on the other hand, we want to reduce the data footprint. So we are going to talk about two results that we have. So this is work of my recent PhD student, Vishalini. And so here what we are looking at is an object recognition problem on power constrained nodes. Okay, so the problem is very simple. That just as we humans do when we look at a particular image, we want to detect objects like dog or bicycle or car and so on, right? So of course, if you are looking at, for example, an intelligent camera in terms of smart traffic or smart transportation, it would want to detect different objects, simultaneously. Okay. So how can we do this? So one of the solutions that is now pretty popular is to use convolutional neural networks. So CNNs are really algorithms, machine learning algorithms that can look at an image, and it can figure out, like, well, this is a boat, with certain probability. So the convolution CNNs have many layers. So here we are seeing different layers. And so typically you have 11 to 15, 16, 18 layers. And it's starting from a detailed image to, as we go, it is abstracting or basically looking at a high level view of objects that it can identify. So a CNN has four different types of layers. The convolutional layer, which is the most computationally intensive layer. And this represents a set of learnable filter kernels. Okay, so it is actually, that's where sort of the intelligence is present, that is trying to find patterns. Okay, and then there is a subsampling type layer. This essentially reduces. Okay, this is trying to reduce the amount of data. So, for example, here, if you have like a 4x4 grid, you could, for example, maybe do a max on 4 contiguous cells, and you got your reduced footprint. Okay. And then the activation layer is essentially trying to introduce some nonlinearity into this feature space. And a common activation function is a ReLU, ReLU. So you have other options too. So we don't have time to go into those details, but ReLU is a common activation function. And lastly, you have a fully connected type of layer where, from one layer to another layer, all the neurons are connected. So the constraint platform that we are looking at is what is known as the PYNQ board. This is from Xilinx. So this is actually using Python. So its programmability is easier. So you can use Python ML code and can map your algorithms onto this board. Okay, and we have because we want to simulate like a constrained node, we powered this through batteries, and we also have measured power consumption through this Keithley power supply equipment. Okay, so where you can plot instantaneous current. So the proposed work is really, the bigger idea is this. So if you have a machine learning algorithm and you want to run that on an edge node, we have to be very smart. We have to dissect the algorithm. So we need to look at like what is the effect of one parameter over your power or delay, and then we can kind of try to come up with parameter values so that that will fit into our budget of power and performance. Okay. So here the first step is that we have dissected the CNN, the convolutional neural network, and what we did was we actually analyzed each type of the layer. Okay, so if I reduce the receptive field size, instead of 11 by 11, like let's say if I go to 5 by 5 or 3 by 3, what happens to the latency? So as expected, of course, the latency went down, power also went down, data footprint also went down. So then next, what you want to ask is, okay, can I live with 5 by 5? What is the accuracy? Okay, can I live with 3 by 3? What is the accuracy, right? Because those are helping us with reducing the footprint as well as power and latency. So I will not be able to go in detail with every optimization, but kind of want to give an overview of what optimizations that we have looked at. So on the convolution layer, for example, like we found that 11 by 11 filter is an overkill. Okay, so we could probably go down to maybe 5 by 5 and still be able to get good accuracy. Now, subsampling layer is a type of layer where there are no learnable parameters, and so this consumes a lot of power as we increase the input dimensions. Okay, so can we reduce the input dimensions? Okay, instead of processing like let's say 10 by 10 image, can I go like 5 by 5, because that directly affects this layer. Now, by the way, the convolution layer is the most computational workload. Okay, so because that's where really the intelligence is. Okay, so so this kind of classification of each layer, what is it important in, what is it doing, and how can we actually be able to. So we want to see we want to see like the effect, and then accordingly we can customize it. Now the network specific optimization. So there are different kinds of learning networks, like LeNet is one, which has a convolutional layer of which has 6 5 by 5 filters and so on, right? So I will not go into details. So those who are working in ML, they know a lot about this. AlexNet is another type of network. So it's not that we have one-stop solution for everything. We have different types of networks, within these deep neural networks. So even this, choosing the right type of network itself can also play a big role. So right on the right hand side here, we kind of looked at like, we analyzed the different network, and we have seen like, okay, you could possibly go from 120 to downsize to 84 neurons, and that still is okay. For AlexNet, you could probably go down to like 256 and so on. There are two other networks, VGG11 and VGG16. So VGG11 is a lighter network compared to VGG16. So what we have done is we found right parameters and right parameters for each of these networks, and this shows like in one slide, like, so the blue is the unoptimized and then the red is the optimized power. Okay, so as we can see that we were able to really reduce the power consumption quite a bit for each of these networks. So we compared, of course, like the question is that, how does it compare with if you were to run this on a desktop where, we have no constraints, is it still comparable? So here, what we see is that the first 4 rows, they have different implementations. Like, for example, the first one is on an FPGA board, but this has 48 GB memory, okay? Whereas on a desktop, this one possibly has like so I'm not sure how much memory we have here, but you can also run GPUs are pretty common. So so on GPU with 6 GB, if you were to run, and then there is a FPGA based implementation. So all this, if you compare, what we see is that the power consumption for our network PYNQ board is about 3 watts. Okay, and compared to like if you were to look at like a GPU, which is 235 watts, or like a Statix 5 FPGA about 27 watts. Also latency, you can see like this is acceptable, like in 9 milliseconds is acceptable, but this is, we are working only with 512 megabytes. Okay, so the inference accuracy was same for all of these above implementations. So we did not lose any accuracy at all. We were able to get the same accuracy, but at a lower latency or reasonable latency and lower power. Okay. So this paper was published in India VLSI conference earlier this year. Okay, so that is the first idea, and really the idea there is that you dissect the machine learning algorithm, look at what are the effect of parameters on your power and performance, and then and also choose the right network and so on. So all this together can really give you a reasonable implementation on a constrained edge node.
Srinivas, 10 minutes.
Thank you, Leon. So the next idea that we have pursued, and this is still work in progress, and this is work of my current PhD student, Lakshmi Kavya Kalyanam. And so this, the idea here is that, okay, you have multiple edge nodes, and these are all in the same vicinity, right? So there are at least a subset of nodes. And because as you can imagine, like if you work in numbers, Unity, you can solve bigger problems, right? So that gave us an idea of how about we do distributed object recognition on multiple edge nodes. Okay, so because you have multiple edge nodes that are sitting next to each other, they can cooperate with each other and try to solve a problem. Okay. So again, here we are looking at a problem of real-time detection of objects in a video stream. Okay, so the network of edge nodes are going to cooperate with each other, and each node is going to run an object detection algorithm. Okay, so each edge node is going to run an algorithm. And the idea is simple. What it is that, okay, you have, let's say, 30 frames coming from the video. Let one of the node act as a master, and let it distribute the workload, to others. So you can send like first frame to first node, second frame to second node, third frame to third node, like that. and then it can collect the results back, So this is the idea, and so this way each node is still working within its constraints, but it's contributing to a bigger problem. So YOLO is one of the popular algorithms that is being used for multiple object detection these days, and I will not go into details. YOLO stands for you look only once. Okay, so in other words, you look at the frame only once and identify the objects immediately. Okay, and I will not go into the details of the algorithm due to time constraints, but it's a very interesting algorithm, and there are variants. So there are variants. Okay. So here we tried two models. One model was there is a load balancer that is running, maybe on a fog node, for example, and the worker node, the nodes basically are going to work with each other, and still you have a head node maybe that has the camera that's sending the frames. Okay, that's model one. Model two is we got rid of the load balancer, another program, and instead the nodes actually can form like either an ad hoc network or they can work on a local Wi-Fi network. Okay. And this is the workflow of how these nodes can work with each other. And by the way, this paper, this work just got accepted at IEEE International Smart Embedded Systems, and it will appear in January. So the experimental results. So we have so YOLO has this tinier YOLO, which is a lightweight version that can be run possibly on edge nodes. And what we have seen is that if you compare, if you run that algorithm on, again, we use the PYNQ board that I talked about earlier as the edge node. And so the time taken, the latency on each of these layers is comparable to running it on an FPGA board or a full-fledged FPGA board or a GPU. And here we evaluated different algorithms. So besides YOLO, there is a binarized neural network or bit neural network. So instead of working with numbers, we work with bits. And this, as you can imagine, is very fast. It's much more faster than this. So we compared with we tried this algorithm as well. And what we found is that this time is really, it's good. Is this is of the order of seconds, whereas this is of the order of milliseconds. Okay, so model one, yes, sorry, yeah, model one, takes more time compared to the model two, which is better, because they are working with each other. And what we have seen is that with tiny YOLO, we can do, like, as we increase the number of worker nodes, we can increase the frame rate. But with bit neural networks, we actually achieve with 3 worker nodes or 3 nodes, we were able to get 19 frames per second. So we are still working on this research to improve the frame rate. But at this moment, if you use YOLO, you can use it on a low frame rate videos. Okay, so conclusions, we can run sophisticated ML algorithms on edge nodes. One is, really dissect and study the effect and optimize. Second is you can do it in a distributed manner. So that's all I have. Thanks for your time.
Thank you very much, Srinivas. I'm waiting for questions from the audience, and while waiting, I'll try to grasp the technical implications of what you're doing. Am I correct in saying that this contributes to reducing the constraints on edge devices?
That is correctly on. So not only can you work with a constraint, right? You can work 2 ways. One is you are given a constraint and you optimize your algorithm for those constraints, right? Or you have an algorithm and you can come up with what would be a good constraint, to achieve a certain frame rate and so on. So you can work in ways as well. Yes. Yeah, and really doing this, we can reduce a lot of data sending, because we don't need to send images. We can send, okay, I found 4 cars, 2 people, in this frame. That's much less data to send to the cloud, right, in real time than sending the image data.
Okay, thank you. And then a second question. I'm not familiar with YOLO, but looking once at a moving object seems to me a bit not tricky, but difficult to identify such an object with a great accuracy.
Oh, sorry. So you only look at once. What that means is that you look at once only at one snapshot at a frame. So if if you have 30 frames per second, you're going to look at each frame, but you only look at once, because image processing algorithms, there are other kind of algorithms where an image has to be reprocessed again and again to find the objects. Okay.
Sorry,
so
that
whereas
was my
here,
ignorance.
one frame, so it is in the passing, and yes.
Thanks. That's a good clarification. I wasn't aware of that. Sorry.
Sure. No worries. Yeah.
I'm seeing no more, which means we are perfectly on time.
Okay.
Thanks a lot, Srinivas, and I'm sure if